This is the team video for project number 22065, Digital to Physical Point Mapping. The sponsor for this project is Raytheon under the direction of Michael Fauch. I am Thomas Fashi. I am the systems engineer and I am the team lead for this project.
I'm Garrett Shea. I'm a mechanical engineer and I'm the procurement lead for the project.
I'm Maddie Novacek and I'm the optical engineer for this project.
I'm Alexandria Taylor. I'm an electrical and computer engineer and I helped with the software.
Hi, I'm Tyler Wong, ECE major, and I am also a software developer.
I am Cedric Bonite, applied physics major, working on software on the project.
The goal, as stated by the sponsor, Raytheon, is to create testing support equipment. Specifically, what they need is a way to reduce the time in order to place accelerometers or other widgets onto complex surfaces such as cars. Ideally, as stated by Raytheon, they want this to be done through the use of 3D models which will have the positions of the widgets already in the 3D models, which will then be portrayed onto the object itself. The concept being used in the creation of this testing equipment can be used in other places as well, such as in construction while building buildings or other weird objects or shapes. It can also be used potentially in a assembly line or other manufacturing, in quality control where it is necessary to determine the correct placement of widgets. After working with Raytheon, we have developed a set of functional requirements that our system must meet in order to fulfill the requirements for this project.
So for the overall design, effectively what we have is a platform that the projector will rest on with two adjustment screws on the back that will allow us to angle the projector to account for the keystone distortion that's built into the projector. That will allow us to project correctly onto flat and non-planar surfaces. We also have a linear mount for two cameras that will allow for adjustment to the left and right, as well as vertical adjustment of those cameras, so that way they can be exactly in line with the projector lens, and we can know the exact distance from the center of that lens to the center of the cameras.
Here's our system block diagram. Our system has 5 subsystems: the UI, imaging, marker, display, and processing subsystem. Each of these systems work together with the user, power supply, and physical object.
We can now go into a more in-depth explanation on the localization algorithm. The localization algorithm uses 2 main strategies in order to find the location of the projector and cameras within our system. We use an image processing algorithm in order to find the QR code, and in combination with a triangulation algorithm, as well as a pinhole camera model, we are able to figure out this information. On the screen, you can see a picture of the image processing algorithm at work, searching for the QR code. Once it does find the QR code, as shown in the image, it will show a green marker and red markers in order to indicate that it did in fact find it, and it found the top left corner marker. After it finds this, we now know the location of the QR code as well as the size of it. So we can then use a pinhole camera model in order to figure out the distance from the camera to the physical object itself. Using multiple QR codes, we can then use a triangulation algorithm to find the exact location of the camera.
In this project, we utilize the Unity game engine, which can be used to create 2D and 3D games, as well as interactive simulations and other experiences. Specifically, we use the Pixies plugin within Unity. This is a special software that is optimized to handle CAD data. Pixies takes CAD data, such as an STP file, and converts it into a 3D tessellated mesh. In other words, it turns CAD data into an object that can be edited within the game engine. The Pixies plugin allows to import any CAD model and enhance the asset using the Pixies toolbox to form a mesh.
We assume that the user will input a single CAD file where the object and the widgets intended to be placed on that object were already specified. The widgets attached to the object are also intended to be non-rigid, with the possibility of having different angular orientations. After inputting the CAD file into a game object in Unity, we added in-game tags to differentiate between widgets and the objects. This was a crucial step as our system focuses on the widgets within the CAD file. Our next step was to apply the wireframe shader script, shown here to determine all the vertices and normal vectors of the widgets, highlight them, and add the coordinates into a list which would later be used for projecting onto the actual physical surface.
Now we will go over some more verification and testing. Here's our first table. As you can see, we had passed all our requirements except for localization testing. This was our first round of testing we did for our project to verify that our system was able to localize objects within 50,000th of an inch tolerance. To do this, we placed 2 QR codes onto a planar surface and mounted the camera and laser rangefinder into our testing rig. We then placed the rig at 5 different distances away from the object. At each of these distances, we took 3 pictures with the camera centered with the QR code and 3 pictures 6 inches to the right of that position. We then used the laser rangefinder to verify the actual distance from the camera to the QR code and compared the results to that of the localization software. As you can see from the verification table, we did fail this test, but if you look at our results, we meet tolerance for both 15 and 20 feet tests. This shows us that our system will meet requirements up to the optimal distance of 20 feet between the camera and the QR code. The next set of verifications relates to distortion. We have met the majority of requirements thus far, but we are still in progress of finishing testing for the mapping accuracy. For mapping accuracy testing, we started by setting up our system facing a planar surface, inputting the necessary parameters into our program, then ran the system and used calipers to measure the dimensions of the projected pixels and compared this to our expected distances. For this round of testing, we met the requirement. We then repeated this, but with the projector tilted 45 degrees from the planar wall. For this round of testing, we also met the requirement. Then again, we repeated this for a cylindrical surface with a known radius. This was our only round of testing where we saw our measurements were over the requirement by about 10,000th of an inch. Because 50,000th is such a tight tolerance and the surface we were using is quite small, this error is to be expected and we'll be running more non-planar testing. This verification testing will continue for another week. Once we get in our 3D printed test surface, we can then finish this test. For our next couple verification tables, you can see we passed all the requirements for the display subsystem and the UI subsystem. Our final verifications that are currently still in progress relates to the integration of our localization and imaging subsystems. This integration is dependent on our other subsystems working correctly, so we cannot complete these steps until our distortion testing is complete. So this will take place in a week.
So originally, what our design started off with was an enclosed box where we would hard mount the projector and 1 camera off to the side. We moved up from there to doing 2 cameras, still in an enclosed box, just to increase our accuracy for localization. From there, we decided that it would be more beneficial to allow the cameras to move and to allow for the potential addition of more cameras. So we exchanged the box for an exterior mounted system, which will be a platform where we can mount cameras on linear rails. And from there, we moved into the same lid platform for the projector with the adjustment screws on the back in order to angle the projector and account for the keystone distortion built into it.
These different iterations of the project were done to help us meet the tolerances set by the requirements of the project. However, even still, we did not meet every single requirement for tolerances. If Raytheon wishes to continue this project, some options for them are to use more cameras and markers in order to increase the accuracy of the localization, or use a laser array or other more precise projection methods.